so I'm happy to introduce Adam Chapala, of course, coming here from just across the river at MIT. And he is, of course, a well-decorated researcher that we have in verification, a wide variety of definitions for verification there in terms of the techniques he uses as well as the systems that he verifies. And I think even most recently, think about one of his particular decorations, he received a Test of Time Award at ICA. Right? And with no further ado, I'll go ahead and let Adam get on to the rest of his talk.
Thank you. Is this loud enough for everybody? Yeah, great. So I'm going to be talking about this particular long-standing idea of doing mathematical proofs about the correctness of software. And I'd like to make this interactive to the extent people have questions during the presentation. Please feel free to jump in. I'll start out by just talking about the way I see this space and the potential for it to improve the way that we build systems, focusing on examples in security at the beginning. And then I'll jump into a particular project we've been doing that demonstrates some of these ideas in practice, and that's in cryptography, as you might guess from the title. And I'll finish up with some speculation on other opportunities to change the way that we design systems based on the fact that we have rigorous proofs of correctness as one of the ingredients. So we're used to dealing with lots of security and privacy problems that pop up regularly in real systems. And the way this usually goes is that we, the honest engineers, build systems, and then the attackers find surprising vulnerabilities in them, and we scramble to add patches that are quite specific to the vulnerabilities that have been found, and we go around the cycle again, and we just keep going, and it's hard to tell when you're done, it's hard to tell where you stand at any point. Part of the reason for that is that the adversary in these scenarios really has an advantage. We as the engineers of systems have to consider all the possible ways that the systems might be attacked. Because if we miss just one of those, then the attacker can go for that one weakness that we failed to secure and can wreck the whole system. And as we think about how to secure our systems, it's fairly common that we can come up with nice, relatively short descriptions of policies we'd like to enforce. Like we can sort of say, what is buffer overflow? And then we want to say, it's never possible to cause one in this system. But then, especially to meet constraints like performance of the system, actual implementations need to put all sorts of complex mitigations in place to implement what seem like relatively simple policies. And this can easily get out of hand, as this picture somewhat illustrates. So another challenge we have is when we build big systems, we typically build them into smaller parts that we can create, debug, and understand separately. And we can do a separate security analysis of every one of the parts of a system. But then, when we plug our parts together, there can be new emergent consequences from the ways that the parts interact with each other. And an attacker can find and exploit a vulnerability that only popped up by plugging pieces together and wasn't there in each of the original pieces. And as we plug more and more pieces together, there's sort of combinatorial more interactions to worry about that might lead to problems. And finally, we might be tempted to go overboard and put so many security mitigations into a system, or even just other features that aren't related to security, that our users get confused how to properly configure the system. And they might act in good faith, but actually go into a very bad part of the configuration space that is hard for us to anticipate, designing a system with all these different features that could be configured in different ways. So, should we give up hope? Is this the way it will always be to implement realistic systems? Given the title of the talk, you probably expect I won't give up hope at this point. I'm going to try to explain the promise of this technique that I'll call end-to-end mechanized proofs of functional correctness, which applies to quite a lot of different kinds of systems, different parts of systems. It's an idea that's been around for at least a few decades, and it's getting more realistic all the time, and I think we're really hitting an inflection point where this could be popping up in industry more frequently. So before I go further, let me try to explain each of these bold-faced terms here so we know what we're dealing with. When I say mechanized proofs, I basically mean proofs checked by algorithms. So the key scenario here is you have a real system, you have its source code, and then you write down a formal specification that captures which behaviors of the system are acceptable to you. Specification should be written as source code in some language. And then you're going to write in another language of source code a proof establishing that your actual system, whose code is given, meets the specification that you've written down. We feed these into a piece of software called a proof assistant, which uses an algorithm to check that the proof is really convincing that the specification holds. The particular proof assistant I usually use is called Coq, which is developed at INRIA in France. There are at least a handful of others that are also used pretty widely. So that was one of the 3 bold-based terms. When I talk about functional correctness, I mean we're not just going to pick a generic property to prove of the system, like it won't crash. We're going to pick a specification that is really quite customized to the system we're studying. For instance, if the system naturally fits a simple take in these inputs, compute these outputs as a function of them kind of model, then we can say the system actually produces the right outputs, whatever the inputs are, and prove that property. And finally, when I talk about end-to-end proofs, this has to do with how it's natural for us to decompose significant systems into multiple pieces or layers, and we can apply this kind of proof style to the individual layers, but even better is then to plug together all the theorems that we've proved to get a top-level, system-level guarantee. And this is sort of some validation that we picked the right theorems to prove for the individual pieces to get to quite often a shorter, easier to believe as reasonable theorem that applies to the whole system, say only talking about the user experience instead of all these internal details. So we can apply this sort of style to all sorts of stacks of components. There's some work that I'm involved with in a project called Science of Deep Specification that's sort of looking at this kind of picture where we are starting with hardware circuits that implement the processors that we were running everything else on, and reasoning about the CPU as a correct bridge of the abstraction between circuits and machine code we want to run. We have compilers we'd like to prove correct that are taking low-level software and turning it into machine code. Higher-level software languages that might get compiled into lower-level languages. We can start connecting this into models of execution that go beyond single machines, and we talk about network protocols at multiple levels. The concrete level of these hosts are sending these messages, and a higher level of trying to implement some ideal world, like some secure setting where we pretend we have a private channel between 2 nodes. It's actually going to be implemented with cryptography at this level, so let's do proofs connecting all of these adjacent stages together, and at the end we have a theorem that says if you run this code on this hardware circuit, it's going to behave as though you were in that ideal world, and we get this nice transitive property connecting all the pieces to each other. So how does this style get around some of the problems that we're all used to from security and privacy today? I started out talking about how the adversary has an inherent advantage in trying to break systems because he only needs to find one flaw to win, whereas we, the defenders, need to consider all the possible attack vectors and block them. The cool thing about committing to functional correctness verification is that you no longer have to be so clever and think of all the possible attacks. In particular, there's a whole family of very serious attacks like buffer overflows and code injection attacks that in some sense, and I'm not going to make fully formal, are going to be impossible if we're able to prove any functional correctness specification for the program. So let me try to explain what I mean by that. I'll start out by reviewing a result that many of us probably saw in an undergraduate theory of computation class. This is called Rice's theorem. It's like a corollary to the famous halting problem undecidability theorem. And it says, imagine any property of program behavior as distinct from a property of program syntax. And I'm going to be kind of fuzzy about what behavior means here, but maybe it means output. So then assume this property is true for at least one possible behavior. It's not a degenerate property that's never going to be happy. And it's false if the program that we're considering doesn't terminate. Then this property is undecidable. And the way we can show that is assume we had an algorithm that decides whether a given piece of program text has a property like this. We're going to use that decider to build a decider for the halting problem, where we are going to take in the code of some program where we need to decide does it halt. We'll actually do some surgery and use that to build a larger program that runs the original, and then afterward run some code that is accepted by the behavior we're interested in, and then passes this program code off to the decider for the original property that is this theorem statement is talking about. So then, if that decider says yes, your program has the property of interest here, then it must be that this program halts so that it can get to this code that we constructed to meet the property up here. And if the decider says, no, your program doesn't have the property that BT has, then this program code must not have finished, because otherwise we would have gotten the BT, and this new program has that property. So basically this means any non-trivial property of program behavior is undecidable. Well, this actually plays to our advantage when we're thinking about security problems. So here's a variant of that kind of theorem. imagine any program specification that you might prove, and I'm going to be really lax here about what functional correctness means. It's going to be broader than functional correctness. It needs to be a spec where there's at least one way to not satisfy the spec. There's at least one program answer that is not okay. So this is way laxer than talking about like my program sorts correctly. There just needs to be one wrong answer at least. Then if you manage to prove that some program meets the specification, then there's no way it suffers from a code injection vulnerability. And here's the hand-wavy kind of proof. Assume that you proved your program, but it still has a code injection vulnerability. Then what the attacker could come in and do is use the code injection attack vector to run his chosen code, which then exits the program early and gives the one wrong answer. So this means if you manage to prove any non-trivial functional correctness property of your program, then you must have had to deal with any possible way someone could come in and run arbitrary code, because arbitrary code is really powerful and it breaks all the interesting specs. We didn't have to think about attack vectors. We didn't even have to think about what code injection means to prove a spec that protects us in this way. So this is like a nice reversal of the traditional adversary advantage. It's still true, we have to be kind of clever in thinking about the full range of attacks that might happen against us, in the sense that very broad categories of ways that that program behavior could be wrong do need to somehow be enumerated in the theorem we proved. For instance, about a year ago, 2 new attacks were disclosed called Meltdown and Spectre, which basically take advantage of surprising interactions within a CPU implementation that can leak information through timing. Well, to be prepared for timing attacks, you would have needed to prove a theorem whose statement mentions timing somewhere. We do need to somehow thread timing considerations throughout the formalization of our system and the theorems we prove about it. But what we don't need to do is anticipate the exact surprising interaction between system components that enable Meltdown and Spectre. We just need to commit to putting timing in all our theorems and concepts like not revealing secrets in all our theorems, and we'll be forced to work through all the potentially surprising interactions of pieces of the system as we make our way to the final proof of the system meeting its spec. And I mentioned how we can have systems with simple security policies that are supported by quite complex mechanisms, and then bugs in the mechanisms actually introduce new security bugs. When we do end-to-end proofs, we gain the advantage that we have to prove a lemma showing the correctness of each of these mechanisms, which are all just used together to prove the theorem that the top-level system meets its policy. So as long as the policy description is short, we can be ready for all sorts of potential mistakes in the other parts of the system, because we'll need to handle the details of those on our path to proving the correctness of the overall system. And I mentioned how when we plug together components, there can be emergent vulnerabilities that weren't there in the original pieces. The nice thing about end-to-end proofs is that all of those connections between pieces are, in a sense, they're implementation details of the system. We don't talk about them in the top-level theorem. So on the path to proving the top-level theorem, we'll have to handle lemmas about the correct interaction of all the internal interface boundaries in the system. So we can actually be guaranteed to find all these bugs, because if there are mistakes there, we will fail to prove some lemma that goes into the top-level theorem about the behavior of our system as a whole. And finally, there are a few benefits that show up even if we don't actually write any formal proof code. If we're considering our system that is gradually accreting complexity through all the mechanisms we're adding for security or other reasons, and then we realize, oh, I actually need to prove every one of these features that I added, then sometimes the nice effect of that is that we realize it's not worth adding a feature, and we just leave it out, but we prove all the rest. And simpler systems are nice, and it's good to have some sort of force pushing back against complexity. And as we even start thinking through, how am I going to prove this system that I assembled? I'm going to work through the map of possibilities, all the weird states my system could get into, just so I can think about how I'll set up this proof. Sometimes just going through that exercise of thinking about how we'll apply formalism leads us to realize there are some problems there before we even start writing the proof, before we even get an algorithm to analyze the proof for us. So these are the reasons why I think this kind of technology is really powerful for both stopping security problems and just for supporting building systems at reasonable cost and not spending so much on debugging and bug fixing in the field and all this stuff. I'm going to transition to talking about one example of a project that I've been involved with recently. But if anyone's been holding on to any questions up to this point, I could stop and answer them now. All right, so here's an example of a sort of hard program to write. This is some code related to elliptic curve cryptography, which is an important part of the cryptographic primitives behind the TLS protocol and others, which you would typically have your web browser speaking each time it connects to an HTTPS URL. And the code here is doing modular arithmetic, modulo rather large prime number, and it's written in a fancy way to get good performance because it's really in the inner loop of a variety of crucial operations and internet servers and browsers and all this stuff. And there's a relatively small set of people on the planet who've learned all the optimizations that folk wisdom says should be applied in implementing this particular kind of modular arithmetic. So the prime number, that's the modulus of arithmetic, is so large that one number mod this prime doesn't fit in any one hardware register. In fact, it doesn't fit in any 1, 2, or 3 hardware registers. So this implementation, as you can sort of see from the structure of the code here, is representing one number split across 5 different registers, basically using a base system whose radix is approximately the size that you can fit in one register. So we go through this arithmetic, and there's a little bit of use of magic numbers and various points. We've got some bitwise operations and sort of non-obvious sequence of steps here, using shifting and anding. And so this is just supposed to implement grade school modular arithmetic, but it's written very carefully to match what commodity processors have available so that this runs quite quickly compared to a naive implementation. We also have to be careful in writing this not to leak secrets through timing, because that's a big concern for cryptographic code. So there are a bunch of different concerns that are being traded off here. So our project is called Fiat Cryptography, and it provides a formal way of generating code like that, along with a proof that is checked by Caw, that the code you generate is actually correct. So we don't need to sweat about writing that code by hand anymore, but yet we get stronger guarantees than the traditional methods have provided. And this is taking place partly within the scope of our DeepSpec project, which you can find at deepspec.org on the web. And we paid for someone to design this logo. Some of you might recognize it as sort of looking like the classic comic Spy vs. Spy, which is, related to cryptography, but it looks like a rooster because a rooster is the logo of Caw, which is the proof tool that we use. All right, so what are we trying to do here? Correct by construction cryptography. Basically, there are 2 key layers of correctness for cryptography. One is an abstract security property, like you need to know the secret key to generate a convincing digital signature. Through a well-established research area called protocol verification, we can connect those properties to mathematical algorithms, which might work directly with huge integers that are impractical to work with directly on our commodity machines. Yeah.
So those aren't the ones you're going to prove, right?
By the end of this slide, I will answer your question.
Okay.
And the second step has to do with implementation correctness, where we somehow wind up with, say, some assembly code that we want to know truly implements this algorithm. And we could address this in the verification style, where we write some code and then prove it. But instead, we're going to follow the synthesis style, where we start with the spec of what we want, and then we automatically generate or derive the code. And in fact, it's this second step that this project I'm talking about deals with. Though there's a lot of interesting work in the first one, too, and it's good to connect these kind of arrows together. And so zooming in on that second part, elliptic curve cryptography is basically about geometry in 2 dimensions, with points whose coordinates are integers modulo some prime number. One of the first tricky parts of implementation is that we switch to a different way of representing points that sort of confusingly introduces more coordinates to make it faster on commodity machines. The operations in the 4-coordinate version use fewer divide and modulus operations, which are really slow on commodity processors. So that's why we switched. And we proved that this optimization is correct. It's really a classic result about the correctness of an abstract data type implementation with a non-obvious data structure. Then we get to zoom in on the individual coordinates, which are just big numbers, and show that we can represent each of those as several integers that are treated as the different digits of some base system representation. And this is just another classic abstract data type proof on a functional program. And then we use some verified compiler ingredients here to take those functional programs and compile them down to efficient low-level code. The moment we output C code in the end, though we're working on getting good assembly code to pop out. And we do some abstract interpretation to infer the right data type for each variable based on what range of values the variable needs to be able to fit. We want the smallest data type that applies to each variable. So we can plug all these arrows together and we get the, or I could call it end-to-end proof, though it's not on the scale of full systems like I was talking about before, connecting the mathematical algorithm to the low-level C code that we're generating. So what exactly are the challenges that we're facing here? The basic reason that interesting implementation challenges pop up here, where if you implement one elliptic curve, you would still have challenges when you go to implement another, is that the key parameter is what is the big prime number that you use as the modulus of arithmetic. And what really shocked me when I first learned about this area is that the experts, when you change the prime number, will re-implement all the code from scratch in assembly language for every interestingly different hardware architecture. They're just applying rules of thumb to do this highly manual work. And what we wanted to do was systematize those rules of thumb so we could build a compiler that does this automatically instead of having people re-implement all the code. So let me try to give a sense for what is different when you change the prime number, or why the properties of the prime modulus matter. Let's take this prime modulus, which is actually one of the most widely used, 2 to the 255 minus 19. It's a mix of having good security properties and being relatively easy to implement efficiently on commodity machines. And this is an instance of a pattern where we have a large power of 2 minus a small constant. So what we might want to get to be fast is a mod operation. This appears a lot in many different algorithms. And let's say we just did a multiplication, where now the result of multiplication has twice the bit width of the bit widths of the inputs. Let's say 2 inputs of the same bit width, multiply them, you've doubled your bit width naively. And we want to apply a mod to shrink this back down to single bit width. So we can have 2 digits, x and y. Y is the higher order digit. We assemble those into the total value of the multiplication result by bit shifting the y appropriately and then adding that to x. And I want to take that result mod, the prime number that is our modulus. So let's do a little bit of algebraic rearrangement. I'll just subtract and then re-add the small constant c in an appropriate place, and then distribute. And now, the modulus we're working with, 2 to the k minus c, appears as a subterm within here. So of course that's congruent to 0, and I can just cross out that part. And now we have this cute little recipe for a mod operation when we know the values of the 2 digits, but only uses 1 plus and 1 multiply. And since c is a constant, we might even compile that into a few pluses and avoid using the multiply instruction of the processor at all. We didn't use any division instruction, we didn't use any mod instruction, which are so slow compared to the instructions that we actually need with this recipe. And this is literally the reason why this prime was chosen, to allow this formula to be used so we get fast implementation on commodity machines. So we want to write some logic that figures this out and explains why it's a sound optimization, and does so for a bunch of other tricks that pop up given your choice of the prime. And actually, this choice influences how we represent one big number as several digits. So assume we're in that modulus, 2 to the 255 minus 19. When we multiply 2 numbers together, the result is naturally 510 bits wide. So we can represent that with 8 different 64-bit digits. Then we can reassemble those digits into the big number by shifting and adding, multiplying, like this formula shows. In this position, that represents how much to shift the higher order digit by, we have shifted by 256 bits. That's really sad, because in the previous slide I showed how things are fast if we're shifting by 255 bits, but we're off by 1, so actually this representation is much slower to implement than others, because it doesn't get to take advantage of the trick that I just showed. So instead, what you'll typically do is break the 510 bits into 10 different digits of bit width 51. And you put these in 64-bit registers and not even use all the bits, because it pays off so much to be able to use the trick from the previous slide. And actually, as we do a series of operations, we'll gradually creep up to using more and more bits before we have to do what's called a carry operation to shrink down to the main number of bits. So basically, every library meant for a 64-bit processor uses this representation. Then we have 32-bit processors out there where we'll take each of those 51-bit digits and break it into what they describe as two 25.5-bit digits, which means digit 1 with 25, digit 2 with 26, digit 3 with 25. You just alternate back and forth like that. So every serious crypto library, every browser for 32-bit platforms will be using this representation. So we already see it's not so obvious how to represent a number. There are at least 3 different reasonable choices just for this modulus. So what we decided to do is build a library that at the highest level, you tell it how to represent a number by breaking it into digits. And then we spit out fast, low-level code. And we'll prove our library sound once and for all, so no matter what choice you throw in at the top, you're guaranteed what comes out the bottom is correct. And if we zoom in on that a little bit more, we have a few layers. One is probably the largest layer, or the one that includes the most trickiness that would be familiar to crypto implementers, is we implement all the arithmetic operations as functional programs over functional data structures. And then we use partial evaluation to specialize those to particular choices of data structure. And now they don't use higher order features, they don't use dynamic allocation anymore. And then we can apply a compilation, a sequence of compilation phases, including inferring bounds for each variable using abstract interpretation, and we can produce low-level C code that we can pretty print. Actually, inside of the Cork proof system, we can make it generate C code as a notation for its own programs, which is a really interesting exercise in using the extensible pretty printing feature. So, just to give an example of one of the algorithms at that top level, let's think about multiplication, where we have 2 numbers we're multiplying, each is represented as 3 digits. And these 2 formulas show how to reassemble the overall number from the values of the digits. And we take all the cross terms and multiplying these 2 sums together, and we line them up so that down each column, the power of 2 that applies is very close together with the other ones. And so this naturally defines a 5-digit representation of the output. We just add down the columns, and we get each of the digits, and this assembles into a very natural 5-digit representation of the output. But we actually want a 3-digit representation to get this to be appropriately using a mod operation. So we use some of the properties like I sketched before, and we can actually move some digits into other positions and get a 3-digit version. The details of this don't matter. This is just a sense of, you can probably imagine spending 5 minutes thinking about this and writing a functional program that does this in a general way. But to do that, we have to think about how we're going to represent numbers as sequences of digits. The most natural way is just to say we're going to fix a base system that is used throughout the code for a particular prime. And we'll just have a weight function that for each one of a series of digits tells us what the weight is, in the sense that when we have a number represented as a list of digits like this one, the first digit is multiplied by weight 0, the second digit is multiplied by weight 1, and so on, and we just add all those together. This actually forces a lot of reasoning about how we avoid getting answers that fit in the available digits and carrying between digits in certain ways. It turned out to be one of the main complexities in the proof as we were building it. So instead, we came up with a different idea, which is we would represent numbers in a more dynamic way, where every number is a list of pairs of numbers, and in every pair, the first component is a weight. It's a value known at compile time that's sort of telling us how much to shift a digit by. And the second component is the actual value of the digit. And we'll actually allow the use of different base systems for different intermediate computations within a larger computation. So now it's just a functional programming exercise, and we can therefore implement operations. Oh, here's a function that will take such a value and interpret it as the number that all the digits represent. So we're representing numbers as lists of pairs of smaller numbers, like this one, digit weight, actual digit value. Here's an audience participation opportunity. If we do that, can anyone think of a really simple implementation of addition for numbers? If we allow duplicate weights in our base system representations, and we allow basically any weights you want, any list of this kind is acceptable as a number. How do we add 2 of them together? Just concatenation will do it, yeah. So we can prove that the evaluation operation distributes over concatenation of lists, and now we have our correct implementation of plus. And multiplication is a little more work. The intuition is compute all the cross terms, like I was showing on an earlier slide. Well, it turns out that's a map nested inside a flat map. So we get to use our usual favorites from functional programming And this is pretty easy to write, and there's a proof in Calc. It's not too bad. It's like probably a page of code to prove the correctness of this implementation. By the way, we can do modular reduction using the trick I had a few slides back, introducing why we would even pick this particular prime modulus. Well, it turns out you can write simple code like this using the list partition function, and it all just kind of works out. We can put it all together to get a top-level modular multiplication operation that takes in two numbers that are tuples of a fixed length that have to follow some base system representation that's just part of the spec. The first thing we do is we convert each of those into our more flexible dynamic list-based representation. And we run the multiply operation from 2 slides back, followed by the reduce operation from 1 slide back, and then convert back out of our strange representation into the standard one. And it turns out to be really pleasant to prove this system. It decomposes nicely into a bunch of different black boxes and lemmas about them. But we then worry if we literally run this using, say, the OCaml compiler, the performance is about 100 times worse than the best known implementation, because we're using lists and higher order functions and features like that that scare low-level system implementers. So the way we get around that, assume we have proved this, and it's just a question of performance. We have this box for, say, that multiply. It has some inputs that are known at compile time, like the digit bit widths, and some inputs that are only known at runtime, like the actual digits, and then it produces the answer. Let's imagine specializing this function to the part that's known at compile time, and then applying partial evaluation to work to reduce away all of that overhead of being generic so that we have code that's quite specialized to this particular set of bit widths, and there's no more use of higher order functions or lists. It's all been flattened down to something that you can squint and see it as C code. And the nice thing about using Calc to do this, the specialized step is just partially applying a curried function. And the reduce step is basically one of the primitives that is in Calc. We use it over and over again in all proofs. When you're proving correctness of functional programs, you always want to partially run the program. So this is very well supported, though there are still some challenges left in getting the best performance for the reduction process. But conceptually, this is a built-in operation. So then we can use those ingredients to, say, phrase the construction of a particular kind of multiply algorithm. This notation is sort of saying, given two input numbers, find an inhabitant of the set of correct answers, which is phrased in terms of an equation that should hold about basically evaluation distributing over your chosen implementation of multiplication. The key important thing is this is phrased in a way where any inhabitant of this type is a correct answer. So we can run the process I sketched on the previous slide, and out pops this formula, which I'm sure you've all eyeballed instantly and identified as correct after applying your stringent standards, and you all like the number 2 here and number 19 here. Well, I agree with you. Yeah, that's the right answer. But it's good to have Calc checking us occasionally. And it's generated automatically, and we can change this to use a different prime modulus and rerun the generation process, and we wouldn't have to think very hard about how it works. It would just turn the crate kind of experience. Yes?
And this is what you want to implement in low-level code?
So
this exact expression?
So this expression works with unbounded mathematical integers. So we have an additional compiler phase that figures out how to implement it with bounded integers by a series of assignments to temporaries where we infer the right C integer type for each temporary to avoid overflows. All right. So we have our implementation, which has a lot of it that's inside of the Calc proof assistant, but also at the very outside in the user experience, we have a Python script that looks at your prime number and makes a guess at the right base system to use. This script could be arbitrarily broken, and we still get correct code to pop out, or we might not terminate if it's really broken in the Python code. But if code comes out, it's correct, it just might have bad performance if the script heuristics made the wrong choice for your particular prime. So we wanted to run experiments. When we say we have this automatic thing that adjusts the parameters, we wanted to run experiments on lots of parameters. So what we did was we automatically scraped the archives of the most popular mailing list for elliptic curves, and we found all the prime numbers that were ever mentioned on it, and we asked our system to generate those. And surprisingly few of those turned out to be really bad ideas that you get terrible code no matter what you do, but we generated those anyway, or our compiler timed out for some of them. So we ran this experiment by generating for all those primes. The x-axis here is how big the prime is in digits, in binary, and the y-axis is the running time for a representative benchmark of an important elliptic curve operation. We're comparing our code against the GNU multi-precision library, which is the previous fastest known generic implementation of arithmetic, big number modular arithmetic. It actually has two versions. One of them is written to be very careful to avoid leaking the number values through timing. The other doesn't have this restriction, so it's often faster for particular inputs. But for both of those versions, we're doing pretty well in comparison, typically in the neighborhood of 2 times to 10 times faster than this implementation by using partial evaluation and also having some tricks that are more customized to particular families of primes that they wouldn't bother to put there. Yeah?
Does your code worry about timing attacks?
We actually generate only straight line code where, by construction, if a program is expressible in our language, it has immunity from timing attacks.
Okay.
But we'd like to do some follow-on work that tackles more of the cryptographic code, which you might not be surprised to hear can't all be straight line. Okay, so this was for 64-bit x86 processors as the target. We actually choose different data structures and algorithms for different platforms like 32-bit ARM mobile devices. So we did some experiments on a mobile phone and using the same code bases, and it's a similar kind of result. And of course, the important thing to remember is all these triangles on the bottom are proved and none of the circles are proved. This was kind of a whimsical kind of experiment to run because there are only a few primes that are used in practice for standardized algorithms. One of them is the 255 minus 19 example I showed. So here's a table showing how our code does in that dimension, and here we are. It's basically the fastest known C code. Actually, for all the elliptic curves that we've tried, we're basically in the equivalence class to fastest known C code, and that's typically comparing against handwritten code. And the assembly can usually beat us, and we'd like to try to fix that by extending our compilation pipeline further down. That's future work. Here's actually the most common elliptic curve. Like if you use the recent Firefox to visit google.com, you're using this one, whereas if you use Chrome, you probably use the previous one. And there we are, like about a factor of 2 off from this fancy handwritten assembly code with vector instructions. Fun fact in this domain, it's really easy to beat OpenSSL's C code because they only work hard on optimizing their assembly code. But we are significantly faster than their C code, which is cross-platform, whereas ours is platform-specific, so it's not a perfect comparison. And most interestingly, our compiler has been adopted for producing the crypto code that goes into Chrome, among others. So it's a library called Boring SSL that Google maintains as an alternative to OpenSSL. If you hit an HTTPS URL in Chrome, it's almost certainly running our code for signature verification and key exchange. The moment we provide the arithmetic code for the 2 most popular elliptic curves, and an internship finished over the summer that, among other things, was trying to get us into the 3rd most popular elliptic curve, and that should come in the next few months sometime. Let's see, so that's the end of the meat of the talk, talking about this project in cryptography. I have some speculation on other fun projects to do after this, but are there any other questions about the crypto project first? Yes?
Yeah, sorry. So how much work is it to like add another curve to Chrome, right? Because it sounds like each curve is, a couple weeks of work, a couple months. Is it just you generate the code and then you convince the Chrome people that you should be adding your code? Is it you generate it and then you run it and make sure everything's all right? Or is it you generate it and then there's a little bit of work to glue it into the...
The concrete problem we had is that with the first roughly production quality version of our compiler pipeline, this one happened to time out the compiler and the others didn't because it's somehow interestingly different from the others. So we've been building a different compiler pipeline with more compile time optimizations.
When you say the compiler, you mean your code generation?
Yeah, I mentioned there's this important part, there's this partial evaluation stage.
Yeah.
That compiler.
Okay.
Okay, any other questions here? All right, and my instructions as a speaker were to expect that about 2:15 people might want to wander to other events, and I won't be offended if anyone does that, but I'll also try to say a bit more about some ideas for future directions. So what's most exciting to me is not just saying, all right, it's a wide world of important code, let's go prove it all. I'd rather reconsider how we should build systems and even make them simpler or otherwise better because we have this kind of mechanized proof available as an ingredient. So I'm interested in redesigning a whole system stack where we just commit to functional correctness proof for every piece, including all the digital hardware components and all the software. and look for opportunities to simplify those pieces as we go through. So this is following an idea called proof-carrying code, where you just refuse to install something if it doesn't come with a proof. So to make this more concrete, we might have this layer of pieces of a system, processors and other hardware at the bottom, operating system runs on that, applications written in a low-level language, functional language on top of that, and then some relational database-style functionality at the top. There are a few places that I have some complaints about the way these pieces typically fit together today. Your functional code talking to the database probably does it by sending strings over a network connection or something, and has to use a clunky fixed query language like SQL, relatively inexpressively. And the compiling from functional code to C-like code, we're typically adding expensive pieces like a garbage collector and other runtime system stuff. The interface of the operating system to that lower level code is relatively complicated because of possibilities for undefined behavior, and there are significant runtime costs based on abstractions like virtual memory and interrupts and so on. And the hardware exposes a relatively unpleasant interface too. For instance, for multi-core systems, there's this morass called weak memory models these days that makes it quite hard to tell what your program is actually going to do. So how might we change some of these interfaces if we commit to proving the correctness of everything? Well, starting from the top, this layer where we connect relational kind of code to functional code, one of our projects called Fiat is looking at allowing programming directly in higher order logic as the equivalent of your query language. And so you can write down any kind of query that you can express logically instead of having to fit into the fixed language of SQL. And to make that work, we built an extensible query planner that will let you add plugins that say, when you see this kind of logical formula, here's how to turn it into functional code. And I proved it's sound, so you can use this idea without having to trust me. And in terms of isolation between pieces, like between the traditional database server and the application, these can all be in one address space because we're just using normal language-based security and encapsulation techniques to make it all work in the original code. At the layer between, where basically we go to implement functional code as low-level code, we're building a different kind of compiler that targets the Bedrock platform, which is like a proof-carrying code multi-language platform, where this compiler is also extensible. You can give it rules that match particular kinds of functional code and explain, well, this imperative code does the same thing. And I've included some manual memory management in the equivalent, so you don't need a garbage collector anymore. And of course, I proved that my rule connecting levels is sound, so you can apply this transformation without having to trust anything I just told you. At the OS interface, we want to be able to write systems code in a language that is a lot simpler than C. It's basically assembly language with control flow and functions and local variables on top. And we don't need a type system because we're going to commit to proving full functional correctness, which kind of subsumes what type systems usually do. So we avoid having to bake one in that then poses restrictions on programmers. And we want our compiler to do worst case execution time analysis. So every function with some annotation help from the programmer, it'll tell you how long it might run for. And then as a result, the operating system needs to do a lot less. It isn't going to apply interrupts to force processes to yield control of the CPU. Instead, we're repeatedly receiving events from the external world and dispatching to functions that you've provided, each of which has promised to run for a certain amount of time. So we just let it go and wait for it to finish. And we also don't need virtual memory because we're inheriting the isolation guarantees from higher levels of the stack, which have all been proved to be maintained throughout the stack. So we no longer need to enforce them at runtime at this point. Yes. And then at this final layer, we are going to expose a simpler language of machine code that has no supervisor instructions, no memory fences, no consequences of weak memory models. Because we will rely on compilers to analyze the functions that are called in response to events from the world to bound which memory objects they might need to touch. And then the hardware is told about this, and before it calls a function, it will ship all the needed memory objects into the local cache of the core that we're running that function on, and then let that function run in a nice simple transaction model where it doesn't see any interleaving with other cores. But we can prove that it it looks as though this call is running atomically, even though it's running at the same time as others that have had disjoint sets of objects shipped into their caches. And so we do this proof at all these levels, and we manage to relate the behavior at this stage up to the higher order logic that we started out with at this stage, which has a much simpler model that doesn't need to know about all these performance concerns. So, summary especially of this last part, a lot of the system design challenges that we're used to as we trade off between concerns like performance and correctness and security get simpler when we commit to requiring proofs of everything. We can move some work that has traditionally been done in runtime enforcement into work for the human proof engineer while developing the correctness argument for some piece of functionality. And this kind of stuff is pretty practical today. We have our code in Chrome where it does a lot of work to run secure web browsing connections. There are a few other examples, and I think we're at an inflection point where there are going to be more and more real-world applications of this sort of stuff every year. And I encourage everyone who isn't already trying this to look into the area. Thanks. Any more questions? Yes.
So you mentioned having nice systems where you have proofs of, for example, resource consumption and so forth. Doesn't that sort of naturally bound the set of problems you can actually solve in the system? Aren't we stuck solving problems that are only as large as will fit in whatever resource bounds we infer?
Let's see. If we have a sound bounds analysis process, then it should give us some sort of bound for any program, and maybe it's just too imprecise to be useful. Is that what you're asking?
Yeah, I'm wondering if there are classes of problems where you just aren't going to be able to solve them that way.
Yeah, there probably are. We haven't even implemented the idea that I was talking about on that slide, so I'm sure that it will not be super broadly applicable to start out with. And then you just have to generalize it somehow, and I'm not sure exactly how. But I think there are going to be a lot of programs that are, I feel like most code is really boring, and this should apply well to boring code. Yeah.
Do you have any challenges related to proving termination of things?
So if we want to do time bounds, then that kind of is strictly harder than termination. And I'm sure there are a lot of challenges there. We haven't really started that part of this yet, so I'm not entirely sure what's going to come up. Yeah.
So between the different layers that you showed in your system diagram, your software, hardware stack, many of those ways that you might want to simplify a system are old in some sense, right? So for example, type-safe operating systems with perhaps embedded languages of some sort, where I don't need to think about hardware mechanisms for process isolation. We can go back 10, 15 years and think about systems that are designed to run C# and Java that delve into that space. Similarly for optimizing programs or extensible compilers. There's work a long time ago from Cobalt, for example, verified frameworks for compiler optimization. Well, what do you think is going to change? I mean, we've seen those techniques before, they seem promising, but I'm curious, like, what about this approach makes these more viable or more tractable or makes it the right time?
Yes, you asked first about using type-safe languages to implement operating systems and extensions to them. Key thing there is that you have a fixed type system, which is relatively inexpressive, which limits what optimizations you can use in your extensions. And a pre-carrying code approach where you can write any machine code you want, as long as you prove that it follows the rules, I think should enable much better performance. And also, it can be done in a way where you get semantic guarantees about the correctness of the system instead of just simple isolation guarantees. And you asked about extensible compilers, where I think the work you mentioned in systems like Cobalt is also relatively limited in what sort of optimizations it can justify. They're classic data flow and abstract interpretation kind of optimizations, and they probably wouldn't work for compiling functional programs into imperative code. That work starts at a lower level than what I was talking about here, so that's probably the crispest description of the difference.
I mean, so one way to characterize it, you think about the logics that previous systems used were just too impoverished to actually do useful things.
Yeah, right, so maybe a type system is one example of logic. And SMT solver-based conditions for correctness of optimizations are another example of a nice automated approach that nonetheless has serious expressiveness limits we'd like to go beyond. Any other questions?
So, I'm sorry.
Okay, let's go. Okay.
Okay, yeah. The only thing you talked to actually mentioned in your approach is trying to actually build some lemmas around very isolated components and trying to build them up. Most out in the wild systems are actually very poorly encapsulated in the first place. So how do you go to actually redesign or try to retrofit your technique into a system that is not designed in the first place to actually work very well in particular? Maybe there's just not enough encapsulation, not enough boundaries to be able to look at it. Just one big top-level theorem, which is just too expensive.
Yeah, sounds like a good question for some work that's important for near-term impact. It's not really one that I'm interested in too much. I like to redesign systems from scratch with proofs in mind. I feel like it tends to pay off in dimensions that would matter even if you weren't trying to do proofs. So, yeah, maybe that's the most I can say. It's a nice benefit to, like I said, using proofs sometimes forces you to write nicer code, and I'm happy to force that benefit down people's throats if they are willing to buy into this. Do you still have your question? No?
No.
Yeah.
From like perhaps somewhat practical point of view, so on one of your first slides, you had these like basically these three components. There's the code, and there's specification, which is also some form of code, and then there's the proof, which again is a piece of code. And obviously that slide would suggest that you have those in three different places. And with something like COP, you're almost certainly forced to have your proof and your proof checking in a place that's different from where you have your code.
Not necessarily.
Certainly when you think about the system.
So most of my projects do put all of those pieces intermixed in single calc source files. You can embed programs of all kinds inside of calc. You can write directly in calc's functional programming language, or you can have embedded domain-specific languages that can be interpreted as the code of, say, low-level systems languages or database languages or even hardware languages. And that all works pretty well to have pipelines where you can fit everything you need in single calc source files and work with it in a unified IDE.
And at the end, you want calc to spit out some C code.
Yeah, which we do by compiling inside of calc and generating a string of C code.
So inside the calc, you have some mechanism that produces the C code, and probably uses something similar to a type system, I guess, or just discussing some logic that you have enforced.
Let's see. We just write a compiler that works with abstract syntax trees after we use various tricks to reify functional programs as abstract syntax trees. It's probably not too different from, say, what Scala metaprogramming systems do and a bunch of other systems out there.
But then the current state of affairs is probably that you get some C code, but that's where your guarantees then end.
True. Yeah, we have other projects that bottom out in hardware descriptions, but you always stop somewhere, and different projects make different choices.
What is your take on like dependently typed languages that kind of like seem to give some promise on integrating these things a bit more tightly?
Yeah, so calc is built on dependently typed language, which I like using for stating theorems and proofs. I think for everyday programming, it's unlikely it's ever going to be worth the complexity, but I could be wrong.
All right, let's thank the speaker.